Hi, it's Tim, and today we're going to run through control systems, see how they're all around us, and the surprising intuitive maths that comes along with them. So first of all, what is a system? It's simply something that, given an input, produces an output. Easy as. So I'll invite you to pause and ponder. Try to think of some systems around you and their corresponding inputs and outputs. Got a few? Some I came up with were the Earth's climate, given inputs like the sun and CO2 and producing outputs like the wind and the temperature. Another would be a musician playing an instrument to give sound of a different pitch or volume. And finally, the analogy that we'll be using today is a car, looking at the accelerator-speed relationship. You'll notice we can be quite loose with our system definitions. It's called a system because it can be a group of different relations. We can lump these all together into a block just by looking at the relationship between input and output. And I've deliberately chosen control systems from many different fields, not just engineering. This is because systems are all around us. And something I like to think about is that living systems are the only things that can change their actions according to the world. So control systems may just be the thing that separates us from rocks. Now, we can describe these systems like everything in the world, with the differential equations describing the rate of change. In our case, we can draw free body diagrams of the forces involved on a car. The net force is the acceleration minus the viscous damping and the inertia. Now, we can solve this as normal using integration, and we may remember that we always get a combination of exponentials and sinusoids, and these are the only things that differentiate to give themselves. But is there a more abstract way of thinking about this? Introducing the Laplace transform. It combines both of the above into a complex number. S is sigma plus j omega. And note I use j's instead of i's because I'm an electrical engineer and we're quirky like that. So sigma is this exponential term, and omega can expand to give sines and cosines, as in the Fourier transform. Now, I won't go into details, but if we apply this transform to our equation, we can write it algebraically with the derivative changing to s, and we can solve it for velocity and isolate the s in the denominator. From here, we can find the inverse Laplace transform to get the time equation for a given force, and we can see that it exponentially rises to a stable speed, which makes sense in a car. We put on the gas and then we rise slowly until we get to our speed. But we can get to a more intuitive understanding of our system by plotting what are called the poles and zeros on the s-plane, with sigma being the x-axis and j omega being the y-axis. This system has a pole where the denominator is 0, or s equals c on m. And we can see the effects of changing these parameters on the response. If we increase the mass of the car, the pole moves to the right, meaning we had a smaller time constant and a slower exponential response, which makes sense as a heavy car takes longer to speed up to the same speed. If we increase the damping, it counterintuitively has the opposite effect. You'd think with more damping it'd be slower, but you'll notice that the steady state value, when time goes to infinity or s goes to 0 as an exponential, decreases, because for the same force you have more resistance, so less ultimate speed. And this makes the system appear quicker as it has less to travel. And you can see this as the pole moves to the left on the plane, meaning a smaller time constant and a quicker exponential. So what we've done so far is open loop control. If we want the right amount of speed, we just press it down on the accelerator the correct amount. But this has some key drawbacks. What if we don't measure the mass of the car or damping properly and we get a wrong model? Or what if we have a disturbance like going up a hill or someone else sitting in the car that changes this force-speed relation? Or what if we're going downhill and it doesn't matter what input we give, the car is just going to exponentially speed up and be an unstable system? Well, we must naturally do this somehow when we drive. We have a target speed, we check the speedometer, and adjust our input on the pedal accordingly. This is closed loop control. Okay, so we apply an input and we subtract the output from our reference. If our speed is less than the target, this sum will be positive and we'll put our foot down on the gas. If we're speeding, the sum is negative and we'll let off the accelerator a little bit. So what we've described is the essence of proportional control. So the gain is proportional to this error signal. But there are two issues. Firstly, as we speed up, we gain inertia. And once we hit our reference speed, even though our input goes to 0, our speed will still go above. And then our error is negative, it'll decrease, then it'll increase. And this oscillation is called overshoot, and may remind you of some of the drivers you drive with. What we can do is add a derivative controller, which is negatively proportional to the error's rate of change. If it's changing too quickly, it will slow down or dampen this response. Secondly, is even if we have a lot of damping, as we saw in the first, this exponential never truly reaches the reference. And poles on the y-axis are an undamped frequency like light or sound, as e to the 0 is 1. And if the combination is on the right-hand side, the positive exponential means that our input will grow to infinity given any input, which we call unstable. So how do we apply this to a real-world system? Well, we'll start by defining what our ideal time response is. Maybe we have a surgical robot where any overshoot would be damaging the tissue, so isn't wanted. Or maybe when your eyes look at something, it doesn't matter if there's a bit of overshoot as long as they're really fast. We can work backwards from this to get the desired closed-loop poles and work out the proportional, integral, and derivative gains from there. So we just covered the tip of the iceberg when it comes to control systems. You may still have some questions like, what about multi-input or multi-output systems like we talked about? Well, we can generalize these using matrices, which we call state space. Or we can cover non-linear systems and even how we can find the optimal control in terms of the input energy. I'll put some links below of great control system playlists if you want to get a better taste. And I want to leave you with a challenge. Think of those systems you came up with at the start and try explaining to someone first if the system is stable or unstable and what the desired step response looks like and maybe how you could even control it with a PID controller. And with that, I'll see you next time. Bye. Okay, let's see.